this time we need to prove it. So that formula is correct. After that, then we need to find a way to discover it. Yeah. All right. So part E.1, verify Fibonacci formula special cases. Yeah. To verify it, at the beginning, we just verify the special cases. So that will be easy. Yeah. Later, we will look at the general case. Yeah. All right. The problem, our computing problem number 10. Yeah. It is just a recurrence relation, a very simple recurrence relation. Yeah. And here, the formula, so here let's bypass the formula discovery step, because that step quite complicated. So let us bypass that step first. Yeah. Someone gave us this formula. Now, f sub n equals 1 over root 5 times big parenthesis, inside the parenthesis, phi to the nth. Phi, that is the golden ratio. Yeah. So remember last time, we find the golden ratio, its value is 1 plus root 5 over 2. Yeah. All right, so then in the big parenthesis, phi to the n minus negative 1 to the nth over phi to the nth. Okay. So this expression, quite unusual. We know Fibonacci number, so remember last time I gave you the approximate value 1.618, and many digits after that. Yeah. Infinite, yeah, actually infinite number. And there is no cycle. Yeah. So this kind of number we call it irrational number. Not rational. So rational number, if it's infinite, you can discover some cycle repeated many, many times. Yeah. But here it is infinite number of digits without any cycle. All right. Yeah. So that's the irrational number. But this irrational number, first you raise to nth power, then minus negative 1 to the nth over phi to the nth, then the whole thing divided by root 5, it becomes an integer. That integer is the Fibonacci number. Yeah. Yeah. So something, if you do not prove it in some special way, it is very hard to believe it, right? So we need to find a way, convincing way to tell us it is correct. So let us do this verification work. Yeah. When we start, we like to verify the simplest cases. Yeah. All right. Step 1, let's look at when n equals 0. Let's plug in. When n equals 0, capital F0, the right-hand side, we plug in phi to the 0, it's 1, right? Yeah. And negative 1 to the 0, also 1. So 1 here, 1 over 1, 1 minus 1, that's 0. So the right-hand side, 0 over root 5, also 0. That's just the same as our base case. F0 equals 0. That's correct. Okay, so the step 1, that is the easiest verification step. Now step 2, when n equals 1. Let's plug in. Is it correct? We need to do some computation here. All right, yeah. Let us use the golden ratio number there. 1 plus 5 over 2, because negative 1 to the 1, it's also negative. Negative becomes positive. Yeah. Then reciprocal, 1 over phi reciprocal, so 2 over 1 plus root 5. Yeah. But here we need to convert it, yeah, because 1 plus root 5 at the denominator, it is not very convenient in our calculation. So we like to change its form. We do transformation on it. How to do it? You know, I believe most of you know how to do it. Yeah. So here I just, you know, write the step a little more. Yeah. We call the rationalization. 1 plus root 5. Can you multiply? Oh, sorry. Yeah. 1 plus root 5. Here there is a conjugate concept. 1 minus root 5. 1 plus, we multiply 1 minus root 5. We call its conjugate of the root 1 plus root 5. Yeah. Because the same number over itself, it is 1. So we do not change its value, right? Yeah. Do simplification, the numerator 1 minus 5, right? Yeah. A, remember here we use the formula A plus B times A minus B equals A squared minus B squared. Okay, so here we apply that formula here at the denominator. So it is 1 minus the root minus 5. Okay, square of root 5, 1 minus 5. The numerator 2 times 1 minus root 5. Okay, then after simplification, 2 over negative 4, 1 minus root 5, right? Yeah. It is a negative, but 1 minus root 5 also negative. So let us change the sign. 1 over 2, use root 5 minus 1 becomes positive. Okay, so that is the form. Yeah. So now we do addition between these two fractions because they have the same denominator 2, and for the numerator, minus 1, 1 cancel out, 2 root 5, right? 2 root 5. Yeah. But you cancel out the 2 at the denominator. So root 5 at the numerator, and this one cancel out with that root 5. So you get 1. Yeah. You get 1. Yeah. Yeah. That's step 2. Yeah. Hope you can see it easily. Yeah. So here you can see we get a F1 equals 1 for our second base case. Yeah. All right. Yeah. Is it enough? Yeah. Yeah. For mathematical induction, it is enough. Yeah. Here we plan to do verification. We plan to use the mathematical induction. Mathematical induction. Let me recall mathematical induction a little bit. Step 1, verify the base cases. We just did it. There are 2 base cases. We verified it is correct. Step 2, make induction assumption. All right. And 3, because it's hard to use simple words to represent it. Let me just say advancing our assumption by 1. Okay, because our assumption, we use a parameter k. Advancing our assumption on k by 1. More specifically, All right, so we will follow. So that means after the base case verification, we do not need to do more cases verification. That's enough. But for our practice here, because doing verification, you need some algebra technique to handle the computation. And I feel for many of you, so probably you're not very strong in this kind of algebra. So I like to do a little more practice. So let us do a few more cases verification. So we just do it, this part as a practice. So case number 3. So let's do one more verification. This time, let's verify F2. Because F2, we know its value. It is also 1, right? 0 plus 1. So its value should be 1. But now we want to check if the right-hand side expression also gives us value 1. So let us use the value. But this time, the golden ratio, the reciprocal part, because -1 squared, that's 1. So we keep this minus sign. And the second term, because we did the, rationalization before, so let us just use that number, replace 1 over phi squared directly. Okay, so so this time we need to do expansion. So when we do expansion, we apply the formula, another formula. So I hope everyone is familiar with it. A plus minus b squared. A plus b squared, A minus b squared. Let me write these two together. A squared plus minus 2ab plus b squared. Okay, so we apply this formula. So we get these two expansion expressions. The same denominator for the numerator part, you can see 2 root 5. No cancellation because, look at that. minus sign, it becomes plus sign, right? Yeah, but 5 cancel out, okay? Yeah, 1 cancel out because this minus sign here, all right? So 2 root 5 plus another 2 root 5, 4 root 5. 4 cancel out the denominator 4. So we get root 5, right? Numerator root 5. Root 5, then external 1 over root 5. Another cancellation for root 5. So you get the answer 1. Yeah. That's also correct. We just verify F2 equals 1. Yeah. So this step number 3 is also correct. Yeah. All right. Yeah. So we did 3 simplest cases verification. Yeah. All right. Next, I like to do another case verification. Yes. Although it's not necessary, but still, we like to do one more practice verification. Okay, yeah. So this time, step number 4, we try to verify F3. Yeah, F3, yeah, because F3 equals F1 plus F2. F1 equals 1, F2 equals 1, so F3 should be, should be 2. All right, let's take a look. If the right-hand side expression gives us value 2. All right, so let's do it. Yeah, but here you can see the degree phi, it's 3, becomes relatively high, right? Relatively high, okay, yeah. Although we can use the usual way, the old way, the way we use in the previous step, yeah. We can use that same way to do verification, yeah. So that is, so more specifically, that is 1 plus root 5 over 2 cube plus, right? Because -1 to the cube, that's also -1, negative, positive. So, and the root 5 minus 1 over 2 cube. Although you can do expansion on these two, when you do, you can use the a plus minus b cube formula, right? Yeah, so let me write cube formula. A cube plus minus 3a squared b plus 3ab squared plus minus b cubed. Okay, yeah, a little more complicated, but if you work slowly, carefully, then you can get the correct answer. Yeah, but here I want to use a different way. Okay, so I do not go, that usual way. Yeah, I try to find a smart way to do it. Yeah. All right. What is that smart way? Yeah. So here, I like to reduce the degree of phi cube. How to reduce it? We know this phi is the golden ratio. It has some very special properties. So we just apply the special properties of phi. Yeah. So let me start with the properties of golden ratio number. Now, there are two properties. The first one, 1 equals phi squared minus phi. The second property, phi squared equals phi plus 1. How do we get it? Why we have these two properties? You may ask me this question. Yeah. The answer is very simple. The answer is very simple because let's recall, how did we find the value of phi? Because we solve a quadratic equation by the quadratic formula. What is that quadratic equation? The original equation for the phi, that is x squared minus x minus 1 equals 0. And we can call phi is a root of this quadratic equation. Yeah. The root means if we plug in phi, the equality should hold. So we should have this identity, equality or identity, okay? This equality, we know it's correct, but we can write in these two equivalent form, okay? Yeah. So you can see if you move 1 from minus 1 term from left-hand side to right-hand side, you get the first property. Then if you move minus phi, minus 1, both from left-hand side to right-hand side, you get second property. Okay, so equivalent expressions. Yeah. But if we use these two forms, yeah, so then it's more convenient in our computation. Okay, all right, so now let's start using these two properties to do the step 4 verification. Yeah. When we start, let us try to reduce the degree of phi cube by using these two properties. Yeah. First, let us write phi cube as phi times phi squared. Okay, so why we split? Because we want to use one of the properties. After the split, you have that phi squared expression. That means we can apply property number 2. Okay, so it becomes phi times phi plus 1. All right, so let us multiply through, so we get phi squared plus phi, but this phi squared, we can apply our second property another time. Yeah, so that is replace phi squared by phi plus 1. So we get 2 phi plus 1 for phi cube. Yeah. This time, the good thing is the degree becomes lower. The degree from original expression, that's 3. After we do transformation, we get the degree becomes 1 here, right? 2 phi, degree 1, 2 phi plus 1. So degree much lower. The lower, the easier in our calculation. Yeah. All right, so that's the phi cube. But there is another term, 1 over phi cube. Yeah, this time, it's a fractional form, a little harder than, phi cube form. Yeah. So this time, we want to do transformation to get a more friendly form. All right. So how to do it? Yeah. 1 at the numerator, But the 1, we can replace it by our property number 1, phi squared minus phi. Yeah. Why we replace 1 by phi squared minus phi? Because we can do cancellation. Cancellation, the common factor cancellation between numerator and the denominator. They have a common factor phi. Okay, yeah. After cancellation, the numerator becomes phi minus 1, denominator becomes phi squared. Okay, yeah, all right. So this time you can see when we do the transformation, we do the equivalent form change on the numerator, not denominator. Yeah, so why? The denominator, we keep the phi to some number, that form, the power form. Yeah. Why? Because that power form is a very friendly form for cancellation. For cancellation, for phi cancellation. Yeah. So we keep that power form. Yeah. All right. Because you should not replace phi squared as a denominator by phi plus 1. Because if you use phi plus 1, it won't be a power form, right? Then it's not friendly for phi cancellation. Yeah. So we keep that power form at a denominator for further cancellation. Yeah. All right. And the numerator, you see 1 another time. Can you replace that 1 by phi squared minus phi again? Yeah. So we can do that substitution another time. After simplification, we get 2 phi minus phi squared as the numerator. So you can see another cancellation, phi cancellation. Okay. Yeah. After cancellation and a little simplification, we have this 2 over phi minus 1. Okay, yeah. Now we feel, so this form, quite simple. Yeah, so we can start to do the, final calculation. Yeah, so let us put those two expressions together for phi cubed plus 1 over phi cubed. Yeah. That is 2 times, yeah, because minus 1 and a plus 1 cancel out. Then we take out common factor 2. So inside parentheses, phi plus phi 1. All right. So when you see this expression, what can you get? What can you get? Because after you multiply 1 over root 5, both sides, 1 plus root 5, both sides, this expression corresponds to F3. This expression corresponds to F1, right? Yeah, F1. All right. That's exactly, we need to check, verify if this equality holds or not. That is, F3 equals 2F1, correct or not? And because we did a computation, F3 equals 2 and F1 equals 1. So this, we know this identity is correct. Okay, so that means our verification using the 2 properties of the golden ratio, we can avoid doing calculation with root 5. Yeah, because when we manipulate golden ratio symbol phi, we never need to use root 5, right? Yeah, so you can see, yeah, a little easier, but a little harder, yeah, because you need to find the right way, smart way to do the transformation here. Okay, yeah, all right. I think that's pretty much enough. Yeah. Yeah, let me see if I do another